Welcome back to Workshop Friend and part 9 of making a radius turning tool for a lathe. Now this really is the final part of this series. It's been a long time, I know, in coming, but in this video we will complete the tool, including making a detachable handle. But the last part of this video is devoted to actually using the tool and finding out what its capabilities and limitations are. So I do hope you will stay right through to the end of the video. First operation is to complete the radius on the keep plate. So that's this 1/4 inch radius on the end here, and that will mean that the keep plate goes into that corner there on the base. So I've got the rotary table on the milling machine. It's on the center line, and I'm just setting up the keep plate to machine this radius. So I've picked up the hole in the keep plate. The radius is actually centered on that hole. And I've also set the stops on the rotary table so I don't have to worry about going too far in each direction. So I'm going to put a small end mill in here now, dial across 1/4 inch, just roughed out that radius so that I don't have to remove all the material with the end mill, because this is a bit of a slow process. It isn't obvious what's going on here, but I'm holding the table firm against one of the stops to complete the straight section which forms a tangent at the end of the radius. So after cleaning up, here is the keep plate, or clamp plate, I'm not quite sure what to call it. So that radius has come out very nicely. It's blended in with that edge there, and I've got the right length. So that now comes in here like that, and you can see it nicely fits with the machined radius. So the next thing to do is to take the table off the base and then drill through these holes using them as a guide. The tapping drill size, I've got 2 head styles. That's the socket head cap screw, which is a little smaller in diameter but taller, and the button head, which is a bit larger in diameter but shallower, and I think is more fitting with this. So I'll try and use these. And I put the table onto some packing here so I can drill right through, and the keep plate is seated in its correct position, so we'll just drill through and tap these holes. And finally, the holes that were originally drilled for tapping size can be opened out to clearance size. So I've deburred everything, given it a thorough clean, and shortened the screws to the correct length, and put a bit of light oil on there. There's a nice smooth action, which is what I was hoping for. The other interesting thing is that the keep plate provides a very efficient locking mechanism. So just the slightest nip on there, and this is rock solid. And that's exactly what I was aiming for. Now the other thing, the pan head screws are definitely the right option as compared with the regular cap head screws. I think they're less likely to trap swarf. They just look the part. And there's just about the right amount of clearance there between the edge of the screws and the dovetail. Now I need to profile the 2 ends of the tangential tool holder and the end of the keep plate. That's going to be a bit of a delicate work holding situation for my lathe. So I'm just going to rough out the edges here, grinding away as much material as possible. Okay, that's the keep plate radius on one end of the tangential tool holder. I put a generous chamfer in here. Now we just need to do the other end of the tangential tool holder. As some of you mentioned, a handle is going to be necessary for this. So before I can test it, I need to make a handle. It needs to be usable from both sides, because sometimes we'll be operating in this orientation and sometimes in the other. The other feature is that it needs to be offset, not in line with this axis, because that will mean that the handle will end up fouling with the chuck or whatever work holding device you have in the lathe. So we want to keep things around to this side, and I think something like 30 degrees from the center line is about right. So I've come up with this drawing. It has a ball handle, and of course we can make the ball handle now, and a bracket. And the bracket sits on the edge and the top of the table, held with 2 screws from the top and 1 screw from the side. Now the 2 screws from the top need to be blind holes, because we don't want swarf dropping down into this mating surface. And I've drawn up the bracket. As you can see here, it's a little bit complicated because it includes this radius. However, I've got a setup now which I think will allow me to machine that quite easily. I've started with a blank, and the blank is necessary to provide material for work holding, so it's a bit longer than I actually need, and I've already machined it to the correct thickness and the correct width, and I've added the 4 holes. So this is the hole for the rod that goes to the ball handle. These are the 2 holes that clamp into the top of the table, and this is the one from the side. So I've got the blank here set up on my angle plate, and I've also got a backing plate here which it just helps with setting up. Now this drill here is also part of the setting up procedure, but I've also made this little arbor which comes in here, and to get the correct radius, basically I measure from the top of here to this known diameter, and that enables me to set this chordal distance. Once I got that correct, I tighten up this plate, and then I can slacken off these 2 and move the work left and right. Now if I remove the arbor, the drill is a nice fit in that hole, and then I can bring the tailstock up with the center and just make sure that the center line of the work is on the center line of the lathe. So I'll know then that I have the center of the work on the center line of the machine, and I'll have the correct radius. So that's the setup, and of course I'm going to be machining this very carefully. I'm also going to put some counterbalance weights in here to make it run a bit smoother and remove that material. And it's reassuring to see that the hole pattern is showing up symmetrically as we break into those holes. So I'm going to keep going, taking about 15 to 20 thou cut at a time, and just taking it very easy. I don't want anything to move. It's also worth noting that that plate on the back here just provides a bit of extra stability to keep things in place. So according to that measurement, we have 6 thou more to come to increase that radius by, and according to my dial I have 5. Well, I believe the 6. I think that's going to be more reliable. When I say the dial, I mean the dial on my cross slide, which I've been tracking. Let's make sure nothing fouls, and then bottom out of the hole, 0 out. I've got to take another 20 thou off the depth as well. And finally, I'm going to use this opportunity to chamfer that inner edge. Okay, we'll see if that fits the top of the table. Yeah, feels like a nice fit. Yeah, I've set the work up on the small rotary table, and I am just radiusing the end of the bracket. I roughed it out first with a hacksaw and on the grinder, offhand grinder, and I'm just finishing off the radius to make it neat and tidy. So you can see here the handle is now complete. It's profiled to sort of match the radius there, and it's removable so it can go on the other side depending on how what configuration you're using. Of course, normally I'd either have this tangential tool holder in place or the regular one. The stem, I had to make a template just to get the bends right, and then finally ended up with the final version here. I didn't in the end make a ball handle, which I could have done because I happened to have this lying around. It was just the right size. I just made a little adapter there, and that's that sorted out. For operation I need 3 Allen keys, the smaller one for these set screws here, the intermediate one for these pan head screws for the handle, and also the locking screws on the keep plate. And so that's that leaves the larger one here for removing the this is regular tool holder and also adjusting its height. I case hardened the handle, this part of the handle, the bracket, and also the keep plate. It would have been nice to case harden the whole thing, but it was just a bit too big, and of course I have a Loctited spigot in the center here, so that wouldn't have been possible. Now all that remains is to machine out this clearance here. If I turn it around this way, it might be clearer. So there's a radius that needs to go in there to provide clearance for larger diameter balls. So I'm going to do that on the lathe itself. Well, it's now time to start testing the radius turning tool in its various configurations. So I'm continuing to turn the aluminium ball, which I started in a previous video, and one change that I've already made is to adjust the angle of this handle here. It was originally 30 degrees from the central line, but I've increased that. I was able to do that by putting this in the press and just increasing that angle, and it just gives me a bit more clearance from the headstock. I think that's probably about an appropriate degree of offset. Now what I'd like to do in this test is to see whether I can part a ball off complete sphere all the way around. So at the moment I'm just putting cuts on with the cross slide. And coming in tighter into the corner on the other side. So I think I'm going to just relieve this here with the parting tool, and then hopefully we can part this ball right off. Not quite parted off, but not far off. This is the drawing of the screw from the machinist jack, which I'm making in another series. And in fact, it was the challenge of making the ball on the end of this which prompted me to make the radius turning tool. Now you can see there that the ball is only 0.313 inch diameter, which is less than 8 millimeters. But the difficulty is it's right up close to this shoulder. So the second test here will be to see if I can actually machine that ball close to this shoulder. Now I was aware that I might have to grind away a little more of the clamping part of the tool holder, as you can see I have done here. That was necessary not for the ball itself, but to clear that larger diameter. So I've done that. I've also thinned the high-speed steel tool slightly, and that gives me just enough clearance to get up tight to that shoulder. So the cutting process is actually quite quick, quicker than I thought it would be. The real time is taken up in setting up the correct radius and making sure that you've got the axial alignment along the shaft correct. I also from time to time zero out the cross slide on the center of the axis, so I know where to go back to if I need to retract the cross slide. The ball has turned out really nicely, as you can see here. This has been machined in mild steel, but I'll be doing it for real in drill rod or silver steel, but I don't anticipate any problems. I've got up close to that shoulder, as you can see here. The profile of the shoulder isn't quite right because I need a narrower parting tool to get into that corner. Another quick modification. While changing out the tool holders and putting this one in, I discovered that these through holes were causing problems with swarf. So I've blanked the bottoms off and Loctited those in and shortened the screws. So for the third test, we've got a 1.5 inch diameter piece of mild steel, and we're going to try to cut a 1.5 inch diameter ball. So I've changed the tool holder over for the other type, and to get the correct radius I'm just going to adjust the cutter until it just touches both sides of the work. So to get the axial position, I just bring the tool up and touch the faced surface of the work, except that that gets in the way. So for 1.5 inch diameter material that doesn't quite work. It's going to be around about there. So we'll lock the table. Let's start hacking this out. Okay, now I've gained some clearance, I can set the axial distance. So we'll just touch the face. It's there. Lock the carriage, and we can continue. Well, that's test number 3. I'm not going to polish it, I'm just going to leave it like that because it shows the finish. I'm sure I can improve that. I haven't gone around the other side because I just didn't want to hack away all that material. I think it proves the point, and there would have been enough clearance to get round quite a long way and complete the ball down to a reasonable diameter shank on the other side. So that's worked fine. Now we're going to do test number 4, which is just to put a radius on a corner. So for that we need to turn the tool holder around for a smaller diameter radius. So this comes off and it's reversed like that. To set the radius, you need to touch off on one side, rotate round, and then we can cut that radius. Okay, that's that done. And finally, cutting an internal radius on the rear of the lathe with the machine running in reverse to get adequate clearance. This was the least successful of the tests. due to lack of clearance around the tool holder, but that could be solved by redesigning the tool holder but keeping the rest of the radius turning tool. Well, that concludes this little project. The radius turning tool isn't perfect, but some of the remaining issues I think can be ironed out. Nevertheless, it's already a useful tool, and I shall be using it in the next video, which takes me back to the machinist jack. I'm almost forgotten all about that, but this tool will be used next video. I hope you'll join me for that. Comments and suggestions, as always, are most welcome.